Good day, everyone. My name is Caitlin Beam, and I will be taking you through the first section of our presentation. So to begin, bridges are fundamental structures that have been used since ancient times, with its precise origin being unclear. Their primary function is to provide passage of obstacles such as bodies of water and rugged or uneven terrain. Early concepts of the bridge were very rudimentary. They were constructed from readily available natural materials such as stones, vines, wooden logs, or date. The structural integrity of these was not high, and as a result, these bridges could not be very large. With time, the design of bridges began to evolve and improve. The invention of concrete and mortar propelled the advancements in structural design and integrity by increasing the overall stability and durability. The Romans in particular were among the first to employ more advanced bridge designs, like the stone arch bridge. Wooden truss bridges were first popularized in Europe in the Middle Ages. The Industrial Revolution then brought about the use of steel as a more durable building material that is still very popular today. There are 7 main categories of bridges: arch, beam, cable stayed, cantilever, suspension, tied arch, and truss. Each category has its own unique set of mechanical principles, but for the sake of this video we will be focusing on the truss bridge. So features of a truss bridge. A truss bridge is a type of bridge configured using the use of trusses. The truss is a structure characterized by a triangulated system of members. These members are set up in such a way that they only incur axial force, that is either tension or compression. This will further be examined in section 2. Here we have some examples of different trusses. Common applications of trusses include bridges, buildings, towers, and roofing structures. There are several advantages of using truss bridges. Some of these being: they are regarded as the strongest type of bridge, they are easy and quick to build, they are relatively light compared to other bridge forms, and they are versatile. There are, however, some disadvantages to the truss bridge. These are: they require precise construction works so that the load can be distributed properly. They require a significant amount of space, especially if they are to sustain larger loads, and they are generally considered less attractive than other bridge forms. This is it for the first section, and I will now pass you on to Aidan.
Good day. My name is Aidan Harrell, and I will be outlining statics and trusses. Statics and trusses form the backbone of civil engineering. Mastery of statics ensures structural equilibrium and safety, while understanding trusses enables efficient load distribution. Statics. Statics is a branch of mechanics that deals with the forces and the effects on bodies of equilibrium. It forms the foundation of structural analysis and design in civil engineering. The key principles of statics are: equilibrium conditions. The sum of all horizontal and vertical forces amount to 0. The sum of all moments about any point is 0. Free body diagrams. Used to visualize all forces acting on a structure or component. Help solving for unknown forces or reactions. Types of forces: applied loads, examples, live loads and dead loads. Support reactions, examples, fixed, roller or hinge supports. Internal forces, examples, tension and compression. Trusses. Trusses are structures composed of straight members connected at joints to form rigid framework. They are primarily used in bridges, roofs and towers to support loads effectively. Key characteristics of trusses are geometric stability. Trusses form triangular units, making them inherently stable. Assumptions: members are connected at pin joints. Loads and reactions are applied only at the joints. Members are either in pure tension or compression. Types of trusses: simple truss, built from a basic triangular unit. Planar truss, all members and joints lie on a singular plane. Space truss, members and joints form a 3D structure. And here we have a simple diagram of a truss bridge. And now we'll be reviewing its members. End posts, the inclined members at both ends of the truss providing support. Top chord, the upper horizontal members under compression. Bottom chord, the lower horizontal members under tension. Diagonal: the slanted members connecting the top and bottom chords managing tension or compression. Vertical: the vertical members transferring loads between the top and bottom chords. Hip vertical: the vertical member closest to the end post supporting diagonal members. Deck: the horizontal platform at the bottom, supporting loads like vehicles and pedestrians. I thank you for your time, and I'll now be handing over to Dominique.
Good day, my name is Dominique Bulu and I will be presenting a weight example of a truss bridge. When analyzing a truss system, it is important to determine the force acting on each of the members. An example of a truss bridge is shown here. We can add the x and y components of the reaction forces at A and E. This is shown in the diagram. The method of joints is the first method. In this method, it is assumed that if the entire truss is held in equilibrium, then each of its joints is also in equilibrium. When a free body diagram is drawn, force equilibrium equations can therefore be used to determine the member forces at each joint. Two equations can be used. The sum of the forces in the x equal to 0 and the sum of the forces in the y equal to 0. The free body diagram for the method of joints is shown here. For the method of joints, the forces at each joint are drawn. In order to determine the sense of direction of an unknown member, it is assumed that all the unknown member forces acting on the joint's free body diagram are in tension. The solutions of the equilibrium equations will give a positive value for members that are in tension and a negative value for members in compression. Once the correct magnitude and sense of an unknown member force is found, it can then be used on further free body diagrams. First, we can determine the values of the reaction forces. This is shown on the screen. Next, we can solve for the forces at joint A. Since both of these forces were found to be in compression, a second free body diagram is drawn to the right of the screen with the correct sense of direction. Solving the forces at joint B, the first free body diagram is shown at the top, and the second with the correct sense is shown at the bottom. Then we can solve for forces at E. Next, we can solve for the forces at D. Since both of these forces were found to be in tension, a second free body diagram is not required. Next, we can solve for the forces at F. Both of these were found to be in tension, and therefore a second free body diagram is not required. Lastly, we can solve for the forces at joint H. The second free body diagram is shown to the bottom of the screen.
Created using Powtoon.
The second method that can be used is the method of sections. In this method, it is assumed that if the entire truss is held in equilibrium, then any segment of the truss is also in equilibrium. An imaginary line can be drawn to cut members of a truss in two to create a section, exposing each internal force as external in the free body diagram. The equations of equilibrium can then be applied to determine the member forces at the divided section. Three independent equilibrium equations can be used. The sum of the forces in the x equal to 0, sum of the forces in the y equal to 0, and the sum of the moments about a point in a certain direction equal to 0. First, we can determine the values of the reaction forces. This is shown on the screen. Next, we can look at the first section. This looks at the forces about joint A. Both of these values are found to be in compression, and therefore the second free body diagram with the correct sense is shown at the bottom of the screen. The next section shows the forces about joint A, H. The second free body diagram is shown to the right of the screen. The third section draws an imaginary line between F and G and C and D and also cuts through C and F. The first free body diagram is shown to the top of the screen and the second to the bottom. This third section looks at the forces about joint E. The second free body diagram is shown to the bottom of the screen. This next section draws an imaginary line between F and G and C and D, and it also cuts through C and F. This next section cuts through G and H, and B and C, and also through C and H. The next section draws an imaginary line between E and F, D and F, and C and D. The last section draws an imaginary line between G and H, C and G, C and F, and C and D. This gives the value of CG to be 0. Thank you for listening to our presentation.
Created using Powtoon.